Welcome! In this session, we'll explore problem number 289, Game of Life. This fascinating problem challenges us to simulate the evolution of a 2D grid based on specific rules governing the states of its cells. Let's dive in and break it down step by step. The Game of Life is a fascinating simulation where we model the evolution of cells on a grid. Imagine an M by N grid, where each cell can be in one of two states, 0, which means the cell is dead, or 1, which means the cell is alive. Over time, these cells change state based on a few simple rules. First, there's the rule of underpopulation. If a live cell has fewer than 2 live neighbors, it dies. This represents a situation where the cell doesn't have enough support to survive. Next, we have the survival rule. If a live cell has 2 or 3 live neighbors, it stays alive, as it has just the right amount of support. On the other hand, if a live cell has more than 3 live neighbors, it dies from overpopulation, as it's overcrowded. Finally, there's the reproduction rule. If a dead cell has exactly 3 live neighbors, it becomes alive, as if new life is created. These rules are applied simultaneously to all cells, and each cell's new state is determined only by its current state and the states of its 8 neighbors, which includes cells directly adjacent and diagonally adjacent. The goal is to implement a function that computes the next state of the grid in place, meaning we modify the input board directly without using extra space for a new grid. The board itself is represented as a 2D array, where each element, denoted as board I, j, corresponds to the state of the cell at row I in column j. As mentioned, each cell can only be in one of two states, 0 for dead or 1 for alive. The task is to update the input board directly so that it reflects the next state of the grid after applying the rules. Let's look at an example to better understand how this works. Consider a board that starts with the configuration 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. After applying the rules to each cell, the board evolves to the following configuration 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0. Notice how each cell's state changes based on the states of its neighbors. This example illustrates the core idea of how the grid transitions from one generation to the next. To understand the output in more detail, let's analyze the first example further. Take the cell at position 0, 0, the top left corner. It has only one live neighbor, so according to the underpopulation rule, it remains dead. Now consider the cell at position 1, 0. This cell has exactly 3 live neighbors, so it becomes alive due to the reproduction rule. Another example is the cell at position 2, 2, which has 3 live neighbors. Since it's already alive and has the right number of neighbors, it remains alive in the next state. By applying these rules systematically to all cells on the board, we arrive at the updated configuration. In another example, for a smaller grid like 1, 1, 1, 0, the board evolves to 1, 1, 1, 1 after applying the rules. Again, the transition is determined entirely by the initial states and the rules of the game. Let's break down the second example to clarify the updates further. For the cell at 0, 0, it has 3 live neighbors, so it remains alive. Similarly, the cell at 1, 1, which starts as dead, also has 3 live neighbors and becomes alive. The rest of the cells are updated according to the same rules. Now, let's address some important constraints and edge cases. The dimensions of the board, M and N, can range from 1 to 25. Each cell state is either 0 or 1, with no other values allowed. For edge cases, consider a board where all cells are dead. It will remain unchanged, as there are no live neighbors to trigger reproduction. On the other hand, if all cells are alive, the board will change significantly due to the overpopulation rule. Special attention is also needed for single-row or single-column boards, where edge cells have fewer neighbors. These considerations ensure our implementation behaves correctly in all scenarios. To tackle the Game of Life problem, we need to simulate the next state of a grid based on a set of rules that depend on the states of neighboring cells. The first approach we considered is the brute force method. Here, we create a separate grid of the same size as the input and compute the next state of each cell by examining its current neighbors. This involves counting all 8 neighbors, including diagonals, to determine whether the cell will live, die, or come to life in the next state. While this approach is straightforward to implement, it comes with a significant drawback. the extra grid requires O(m*n) space, which isn't optimal for large grids. Additionally, although the time complexity remains O(m*n), since every cell is processed individually, the additional memory usage makes this method less efficient for larger boards. This simplicity is a trade-off against memory efficiency, prompting the need for better strategies. An alternative and more efficient method is the in-place state encoding approach. Instead of using an extra grid, we modify the input grid directly to encode intermediate states. Since each cell can only be alive or dead, we can use unused integers to represent transitions. For example, we use the value 2 to indicate a cell that was alive but will die, and the value 3 to indicate a cell that was dead but will come to life. After processing all cells, we decode these intermediate states back to their final values of 0 or 1. This method reduces space complexity to O(1), because no additional storage is needed. The time complexity remains O(m*n), as each cell is still processed once. The key realization here is that the input grid itself can act as temporary storage, enabling in-place computation without wasting memory. While slightly more complex than brute force, this method is both elegant and memory efficient. Another idea we considered is a recursive or backtracking approach, which theoretically simulates transitions through recursive calls. However, this method is impractical for larger grids due to its inefficiency and the risk of stack overflow when dealing with deep recursion, especially in grids with larger dimensions. The in-place state encoding approach was ultimately chosen because it offers the best balance between efficiency and simplicity. By encoding intermediate states directly into the input grid, we achieve a space complexity of O(1), which is crucial for handling larger grids. The implementation remains relatively simple, as counting the neighbors follows the same logic as other methods, and the encoding and decoding steps are minimal. Furthermore, this approach scales well, maintaining an O(m*n) time complexity regardless of grid size. A key insight that guided this choice is the realization that only the 8 neighbors of a cell influence its state, allowing us to efficiently compute transitions without extra memory. The problem naturally lends itself to 2 distinct passes, one to calculate and encode state transitions and another to decode the grid back to its final state. This separation streamlines the logic and makes the solution clearer. Additionally, since the rules of the game of life are local to each cell, modifying the grid in place aligns perfectly with the problem's requirements, making this approach particularly well suited. Each approach we considered comes with its own trade-offs. The brute force method, while simple to implement, relies on an extra grid, which unnecessarily increases memory usage. On the other hand, the in-place encoding approach requires slightly more effort due to the need for encoding and decoding transitions, but it is far more memory efficient and scalable, making it the best option for large grids. The recursive approach, though theoretically interesting, is not practical due to its inefficiency and the risks associated with deep recursion, such as stack overflow. Ultimately, the in-place encoding method stands out as the most efficient and scalable solution to this problem. It strikes the right balance between clarity, performance, and memory usage, making it an excellent choice for solving the game of life effectively. The game of life problem is centered around simulating the evolution of a two-dimensional grid, where each cell is either alive, represented by 1, or dead, represented by 0. The state of a cell changes based on the states of its 8 neighbors. For instance, a live cell with fewer than 2 live neighbors dies due to underpopulation, while one with 2 or 3 live neighbors survives to the next generation. On the other hand, a live cell with more than 3 live neighbors dies due to overpopulation, and a dead cell with exactly 3 live neighbors becomes alive through reproduction. To solve this problem efficiently, we start by representing the grid as a 2D list of integers, where each element corresponds to the state of a cell. In this representation, the grid has m rows and n columns. Next, we focus on counting the number of live neighbors for each cell by defining the relative positions of the 8 possible neighbors, including top, bottom, left, right, and diagonals. This neighbor counting step is essential to determine the transitions in each cell's state. When counting neighbors, we need to be careful to skip any positions that are out of bounds to avoid index errors. Once we have the neighbor count, we apply the rules of the game to determine the next state of each cell. However, directly updating the grid in place can lead to premature overwrites of data. To address this, we use a temporary encoding scheme to store both the current and next states within the same grid. This encoding works as follows: if a cell transitions from dead to dead, it remains 0, and if it stays alive, it remains 1. If a live cell dies, it is temporarily marked as 2, and if a dead cell comes to life, it is temporarily marked as 3. After processing all cells, we decode these temporary states to finalize the grid update. Specifically, we convert 0 and 2 back to 0, representing dead cells, and 1 and 3 back to 1, representing live cells. By the end of this process, the grid is updated in place, and the resulting grid can be returned as the output. One of the key insights of this approach is the use of in-place updates with encoding. This eliminates the need for creating a separate grid, thereby saving memory. The temporary encoding ensures that both the old and new states of a cell can coexist during computation. Another important optimization is the efficient counting of neighbors. By using relative positions stored in a simple list of tuples, we avoid recalculating neighbor positions repeatedly. Iterating through the grid ensures that each cell and its neighbors are visited exactly once, leading to an overall time complexity of O(m*n), where m and n are the dimensions of the grid. Special care is needed for edge and corner cells to ensure neighbor positions remain within bounds. The grid itself is the primary data structure, storing both the state of each cell and its encoded transition. Additionally, the list of offsets simplifies neighbor calculations, as we can directly iterate over these relative positions. Together, these choices allow the algorithm to be both time and space efficient. To implement the solution, we define the relative directions of neighbors as a list of tuples and iterate over each cell in the grid. For each cell, we initialize a count of live neighbors and check all 8 possible neighbor positions. If a neighbor is within bounds and is currently alive or marked as alive to dead, encoded as 2, we increment the live neighbor count. Based on this count, we apply the rules of the game. If the current cell is alive, it dies if it has fewer than 2 or more than 3 live neighbors, which we encode as 2. If the cell is dead and has exactly 3 live neighbors, it becomes alive, which we encode as 3. After processing all cells, we finalize the grid by iterating through it again and decoding the temporary states. This is done using the modulo operator, where 0 and 2 become 0, and 1 and 3 become 1. The result is a fully updated grid that represents the next state of the system. This approach ensures that the algorithm runs in O(m*n) time and uses O(1) additional space. Let's walk through an example to see the algorithm in action. Consider a grid with 3 rows and 3 columns, where the initial state is as follows: the middle column contains live cells, and the rest are dead. First, we calculate the live neighbors for each cell. Using this information, we apply the rules and encode the state transitions. For instance, the top middle and bottom middle cells die due to underpopulation, encoded as 2, while the middle left and middle right cells come to life, encoded as 3. The resulting encoded grid reflects these transitions. Finally, we decode the grid back to its final state, where the middle row forms a horizontal line of live cells, and the rest are dead. This example illustrates how the algorithm efficiently handles transitions and updates the grid in place to simulate the next state of the game of life. Here, we start by defining the game of life function within a class called solution. The function takes the board as input, which represents the current state of the grid. To begin, we calculate the number of rows and columns in the board. Then, there's a nested helper function called count_live_neighbors, which calculates the number of live neighbors for a given cell. This function uses a list of directions that represent all 8 possible neighbors around a cell. By iterating through these directions, we calculate the row and column indices of each neighbor and ensure they are within bounds of the board. If a neighboring cell is alive, which is indicated by its value being 1 or -1, we'll discuss the significance of -1 shortly, we increment the count. After defining this helper function, we loop through every cell in the grid. For each cell, we calculate the number of live neighbors using count_live_neighbors. Then, we apply the rules of the game of life. For instance, if the cell is currently alive and has fewer than 2 or more than 3 live neighbors, it dies due to underpopulation or overpopulation, respectively. To mark this transition, we set the cell's value to -1, indicating it was alive but is now dead. Now, we handle the case where a dead cell becomes alive. According to the rules, if a dead cell has exactly 3 live neighbors, it transitions to the alive state. To mark this, we set its value to 2, which indicates it was dead but is now alive. Once we've processed all cells and marked their transitions, we need to finalize the board. This is done in a second loop through all the cells, where we update the board based on the temporary values we used earlier. Cells marked as -1 are updated to 0, meaning they are now dead. Similarly, cells marked as 2 are updated to 1, indicating they are now alive. This ensures the board reflects the next state of the game of life after applying all the rules. By the end of this process, the grid is updated in place, and we've successfully implemented the game of life in Python. Here, we start by defining the game of life method, which takes a 2D array called board as input. This array represents the grid where each cell is either alive, marked as 1, or dead, marked as 0. First, we determine the number of rows and columns in the grid using board.length and board.0.length. Next, we define a two-dimensional array named directions that contains the relative positions of all 8 possible neighbors for any given cell. These include diagonal, horizontal, and vertical neighbors. Now, we begin iterating over each cell in the grid using 2 nested loops, one for rows and another for columns. For every cell, we initialize a variable called liveNeighbors to 0, which will keep track of the number of live cells surrounding the current cell. Inside this loop, we use a for each loop to go through each direction in the directions array. For each direction, we calculate the row and column indices of the neighboring cell as nr and nc. Before counting a neighbor as live, we ensure that it is within the grid bounds and check if its value is 1 or -1, the latter indicating a cell that was live but is now marked to die. This ensures we count valid live neighbors accurately. Next, we apply the rules of the game to determine the new state of the current cell. If the cell is currently alive, indicated by a value of 1, and it has fewer than 2 or more than 3 live neighbors, it dies due to underpopulation or overpopulation. To mark this transition, we set its value to -1, which means was live, now dead. On the other hand, if the cell is currently dead, indicated by a value of 0, and it has exactly 3 live neighbors, it becomes alive due to reproduction. We mark this transition by setting its value to 2, which means was dead, now live. After applying these rules to all cells, we need to finalize the board by updating the states to their new values. This is done with another set of nested loops where we iterate over each cell again. If a cell's value is -1, we set it to 0 to mark it as dead. If a cell's value is 2, we set it to 1 to mark it as alive. This ensures that the board is updated to reflect the next generation of cells, and the transitions are complete. Let's begin with a simple 2x2 board. The input board has 2 live cells in the first row and 1 live cell in the first column of the second row. The first step is to count the live neighbors for each cell. For cell 0, 0, its live neighbors are the cells at 0, 1, and 1, 0, giving a total of 2. Similarly, cell 0, 1 also has 2 live neighbors, which are 0, 0, and 1, 0. For cell 1, 0, we count 0, 0, and 0, 1 as neighbors, so it also has 2 live neighbors. Lastly, cell 1, 1 has neighbors 0, 0, 0, 1, and 1, 0, resulting in 3 live neighbors. After counting, we apply the game of life rules to determine the cell states. Since all the cells except 1, 1 have exactly 2 live neighbors, they stay in their current state. Cell 1, 1, which was dead, becomes alive because it has exactly 3 live neighbors. To differentiate this change, we mark it as 2 temporarily. Now we move to the finalization step for the 2x2 board. Here, we update the marked cells. Cell 1, 1, which was marked as 2 to indicate it will become alive, is finalized by converting its state to 1. The resulting output is a board where all cells are alive. Shifting to a larger 3x3 board example, we start again with the first step, counting live neighbors. In this case, the input board has a live cell at the center surrounded by other live cells in a cross pattern. We'll count the live neighbors for each cell to understand how the rules will apply. For the 3x3 board, we calculate the live neighbors for each cell. Cell 0, 0 has 3 live neighbors, which are 0, 1, 1, 0, and 1, 1. Similarly, cell 0, 1, being surrounded by live cells, also has 3 live neighbors. Cell 0, 2 has 3 as well, and the same applies to cells 1, 0, 1, 2, 2, 0, 2, 1, and 2, 2. However, cell 1, 1, the center cell, has 4 live neighbors, which is one more than the threshold for overpopulation. With the neighbor counts determined, we apply the rules to update the states. Cells like 0, 0, 0, 2, 2, 0, and 2, 2, which are currently dead but have exactly 3 live neighbors, will become alive and are marked as 2. Cells that remain alive, like 0, 1, 1, 0, 1, 2, and 2, 1, stay unchanged. However, the center cell, 1, 1, will die due to overpopulation, so it's marked as -1. To finalize the state of the 3x3 board, we update all marked cells. Any cell marked as 2 becomes alive, so we convert those to 1. Similarly, any cell marked as -1 becomes dead, so it is updated to 0. After this step, the board transforms into a state where the outer edges are all alive, while the center cell is dead. This results in a balanced configuration where no further overpopulation or underpopulation occurs. Finally, let's consider an edge case where the board consists of all dead cells. In the edge case with a 3x3 board of all dead cells, the first step shows that all cells have 0 live neighbors since there are no live cells on the board. Applying the game of life rules, no changes occur because no dead cell has exactly 3 live neighbors to become alive. As a result, the output remains the same as the input, with all cells staying dead. This demonstrates how the rules handle scenarios where no activity exists on the board, maintaining the stability of the system. To analyze the time complexity of the game of life function, we start by examining the operations performed on each cell of the board. First, when counting live neighbors, the count_live_neighbors function is called for every cell, RC. This function checks up to 8 neighboring cells using the predefined directions array. Each neighbor check involves simple operations like boundary checking and conditional evaluations, all of which are constant time operations. As there are always 8 neighbors to consider, the complexity of this step for a single cell is O(1). Next, the algorithm iterates through all the cells of the board, which amounts to rows*calls iterations. Since the count_live_neighbors function is called for each cell, the total time spent on neighbor counting is O rows*calls. After counting, the board is updated in place. Updating each cell involves another constant time operation, and since every cell is visited, this step also takes O rows*calls. The next step in the algorithm is finalizing the board. This involves making a second pass over all the cells to finalize their states based on the calculated updates. Once again, this involves constant time operations per cell, and with rows*calls cells, the time complexity for this step is also O rows*calls. Combining these steps, the total time complexity of the algorithm is derived. Counting neighbors contributes O rows*calls, and updating and finalizing the board each contribute O rows*calls, resulting in a total time complexity of O rows*calls. This makes the algorithm efficient in terms of its runtime for boards of varying sizes, as the complexity scales linearly with the number of cells in the board. Now turning to the space complexity, we focus on the memory used during the execution of the game of life function. The algorithm updates the input board directly, which means no additional space is allocated for creating a copy of the board. This in-place update significantly reduces memory usage. Additionally, the directions array, which is used to define the possible neighbor offsets, contains a constant number of elements, 8 pairs of integers, making this a fixed O(1) space requirement. Beyond this, the function uses a few scalar variables, such as rows, calls, and iterators like R and C, which also occupy constant space. Since there is no recursion in this implementation, no extra stack space is used. Therefore, the overall space complexity of the algorithm is O(1), meaning it operates with a constant amount of memory regardless of the size of the board. When comparing this optimized approach to a brute force method, the advantages become clear. A naive solution might involve creating a separate copy of the board to store the updated states while iterating through the original board. This would increase the space complexity to O rows*calls, as the additional memory would scale with the size of the board. In contrast, the game of life function avoids this overhead by utilizing in-place updates, which maintain the space complexity at O(1). Regarding time complexity, both the naive approach and the in-place approach require O rows*calls time, as every cell and its neighbors must be processed in both cases. However, the in-place method achieves this without sacrificing runtime efficiency, while optimizing memory usage, making it a more resource-efficient solution overall. To formally solidify the time and space complexity, we can break down the operations mathematically. First, neighbor counting involves checking up to 8 neighbors for each cell, which is a constant time operation. Since this is done 4 rows asterisk calls cells, it results in O rows asterisk calls time. Next, updating the board involves iterating through the same rows asterisk calls cells, with each update performed in constant time, leading to another O rows asterisk calls. Finally, a second pass is made to finalize the states of all cells, which also takes O rows asterisk calls. Adding these together, the total time complexity remains O rows asterisk calls. On the space side, no additional memory is used apart from a constant amount for helper variables like the directions array and scalar variables, resulting in an O(1) space complexity. This mathematical breakdown confirms that the algorithm is both time efficient and memory efficient. When tackling the game of life problem, there are some common mistakes that can trip you up if you're not careful. One frequent issue is modifying the grid while you're iterating over it. If you update a cell directly, those changes can affect the computation of neighboring cells, leading to incorrect results. To avoid this, you can either use a temporary grid to store the next state or encode transitions directly in the existing grid by using intermediate states. For example, you can use 2 to represent a cell transitioning from live to dead, or -1 for a dead cell transitioning to live. Another common mistake is calculating the neighbor count incorrectly, especially at the edges or corners of the grid. To handle this, it's helpful to define a list of relative positions for the 8 neighbors and ensure you always check that indices stay within bounds. Finally, inefficient neighbor traversal is another pitfall. If you recalculate neighbors for each cell naively, it can add unnecessary overhead. Instead, predefine those relative positions and reuse them to streamline the process. Another mistake to watch out for is confusion between the live and dead states. It's easy to misapply rules, such as using the overpopulation or underpopulation conditions for cells that are already dead. The key here is to separate the logic for live cells and dead cells clearly in your implementation. Testing your code against simple edge cases can help verify that your logic is correct. Overcomplicating the solution is another trap. Some people try to introduce advanced algorithms, like recursion or dynamic programming, which are unnecessary for this problem. The rules are straightforward, so it's best to stay focused on the core problem and implement a clean, efficient solution. Simplicity is often the key to success here. In interviews, clarity is one of the most important things to focus on when solving the game of life problem. Being able to explain how you transition states and calculate neighbors is crucial, and visual aids like diagrams can be very effective. You should also be prepared to discuss space optimization. For instance, you can explain the trade-offs between using an auxiliary grid versus encoding state transitions in place. Testing edge cases is another area where interviewers often probe. Make sure you can handle scenarios like a grid that's entirely live, entirely dead, or contains only a single row or column. Lastly, be ready to discuss time complexity. The solution typically runs in O(m*n) time, where m and n are the grid dimensions, and this is optimal for the problem. Explaining why this is the case will demonstrate a solid grasp of algorithmic efficiency. The game of life problem has some interesting connections to other problems that you might encounter. For instance, LeetCode 73, set matrix zeros, involves similar in-place matrix manipulation techniques. The original game of life problem itself is, of course, a reference point. Spiral matrix, LeetCode 54, is another grid traversal problem, and LeetCode 200, number of islands, involves counting connected components in a grid, which shares some conceptual similarities. In terms of alternative approaches to solving the problem, you can either use in-place state encoding or an auxiliary grid. With in-place encoding, you use intermediate values like 2 or -1 to save space, but this can make the solution harder to debug. On the other hand, using an auxiliary grid is easier to implement and debug but comes at the cost of additional space usage, specifically O(m*n). Choosing the right approach depends on the problem constraints and your priorities. Another advanced technique you can explore is bit manipulation. Here, you use bits in an integer to store both the current state and the next state of each cell. This is a clever way to save space, as it avoids the need for a separate grid or even intermediate values. However, the trade-off is increased code complexity, as managing bits can make the implementation harder to read and debug. This approach might be worth considering if space optimization is critical, but it's important to weigh that against the added difficulty in maintaining and explaining your solution. Ultimately, the best approach depends on the specific requirements of the problem and the context in which you're solving it. Great job! To wrap up, we reviewed how to simulate the game of life problem efficiently, discussed key takeaways like understanding grid-based algorithms, and highlighted its relevance in coding interviews. Thanks for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!